afternoon. Can I have it a little louder? Thank you. Good afternoon. Okay, all three of you, good afternoon. Okay, it's the last week of instructions, and I will hold review lecture on Monday in a week, and on Wednesday in a week from 1 to 2 o'clock. There will be no morning lecture in the R&R session. And I will on Friday, the last one before the final, I will hold a lecture about Berkeley and the actinides. These actinides are this group down here in the periodic system that are sort of lost there on the bottom. And I bet you some of your teachers in high school never told you about this. And I will tell you about this because there are elements like berkelium and californium and einsteinium and americium for America and curium. And so I will tell you all about this, about the history of these actinides and how Berkeley is related to that. Most of them were discovered at Berkeley by a guy called Seaborg, Len T. Seaborg. He had his 100th anniversary of his birthday on Thursday. And we had a symposium on Saturday for him, a huge symposium. And we commemorated his birth and his great science and political and humanistic achievements. So then the final will be at 8 o'clock, I understand, on the, what's the date? The what? Then Wednesday the 9th, thank you, will be at 8 o'clock. And there will be 3 hours for you. There will be a total of 60 questions. Each question is worth 4 points. About 40% of the will be covered for what we had since the last midterm and now. And between midterm, the first midterm, second midterm, and third midterm will be each about 20%. So you need to know everything, okay? You have the last homework was posted this morning, or you could access it this morning. And can you hear me in the back there? Can you hear me? Good, thank you. So that is due on Monday. And that's Monday morning. Essentially, the R&R session has started, and I can't give you any work or new stuff during R&R week. So if you would prefer, I could make this Friday night, midnight, do the homework. But if you are fine with this, I'll leave it as Monday. But if you said, no, you're violating the rule, you have to put this on Friday night, midnight. So what do you prefer? Leave it? Monday. Okay, good. Thank you. I have it on record now. All right. So today we're going to talk about redox chemistry and electrochemistry. You heard of redox chemistry. Redox means reduction and oxidation. So one thing gets reduced, the other oxidizes. And these are called redox reactions. And we're going to dive into this a little bit more in detail. But first, I want to recapitulate for you what an oxidation number or an oxidation state is. You remember what a formal charge is? At a formal charge, we drew the Lewis structure, and we divided the bonding electrons between the bonding partners equally, and then we compared the number of electrons that they had when after that division to the neutral atom. And then we defined the formal charge this way. There's something similar with the oxidation number, or it's also called frequently the oxidation state. So if you look at this molecule here, NO2 minus, so this is the Lewis structure. There we divide up the electrons so that, in order to determine the oxidation number, we divide the electrons so that the more electronegative one gets all the electrons, okay, except unpaired electrons. They stay with that molecule, with that atom. So if you would do that, the oxygen would be 2, 4, 6, 8 electrons it would have here, and it has 2, 4, 6, 8 electrons here, and the nitrogen would have how many electrons left? 2 left, okay? Now we divide up these electrons, the nitrogen has 2 and the oxygen has 8, and then we compare this to the atom. The atom in nitrogen, how many electrons does it have? 5, okay? And the oxygen has? Oxygen, how many electrons? 6, okay, good. And so now we say, this here has given off 3 electrons, okay? So it has 3 electrons less, so it's a positive because the charge we lost charge is positive. So what do you think? It's plus something? What would you think it is? Plus 3. The oxidation number is plus 3, or we call it oxidation state 3, plus 3. Now the oxygen, what would that be? It's 6 compared to 8, so that must be minus because it has 2 more electrons, and with this the oxidation number would be minus 2, okay? And we will be using this quite a bit when we are doing redox reactions. So we are losing electrons, one compound loses electrons, or one element loses electrons, and the other one gains them, all right? And with this the oxidation number changes, because if this gains, for example, 3 electrons, what is the oxidation number then? 0, okay? And if this one loses 2 electrons, what's the oxidation number? 0, exactly, very good. So now, let's pay close attention. Leo goes grrrr. There, I can see your mind. Now he lost it. The old professor up there, he was on the edge always a little bit, obviously, but now he lost it. No, he hasn't lost it, okay? He's giving you a mnemonic to remember oxidation and reduction. Loss of electron is oxidation. Loss of electron is oxidation. Leo, loss of electron is oxidation. Goes grr. Gain of electrons is reduction. Leo goes grr. Leo goes grr, okay? Wait, timid Leo. So this is how you can remember when a compound gains electron, then a compound gets reduced from a high oxidation state to a low oxidation state. When that compound loses electrons or gives off electrons, so it goes from a low oxidation to a high oxidation state because they've given off these electrons. You're with me? All 3 of you? Okay, good. All right. Just kidding. So there are people who are not so much friendly towards animals. They have ambivalent towards animals, and especially pets. So we do that then. Oil rig. And this is very fitting with our current economy. If we keep going like this, we won't have any oil soon anymore, and then we are really in trouble. But this is going to be your problem. We just started this. Your parents and grandparents, they just started it, okay? Great. So you will have to deal with this. Oil rig means oxidation is loss. Oxidation is loss. And reduction is gain. Rig is reduction is gain. Oil rig of electrons, okay? So you can memorize both of them or one or the other. Don't mix them up too. All right, so we have set now the foundation to understand a couple of things that I'm trying to talk about today. So you have zinc metal. What's the oxidation state of zinc metal? Zinc is zinc metal. What's the oxidation state? What's the oxidation state of zinc metal? 0. What's the oxidation state of copper metal? What's the oxidation state of zinc 2 plus ions? What's the oxidation state? It says right there, 2 plus. Okay, it lost 2 electrons, so it's twice positive. Oxidation state is 2 plus. What's the oxidation state of copper 2 plus ions? 2 plus, excellent. What's the oxidation state of zinc metal? Oxidation state of copper metal? Oxidation state of gold metal? Okay, excellent. Alrighty, so you're more awake than the guys in the morning. So now let's assume we have zinc sulfate, that's a salt. you have a beaker of water, and you put zinc sulfate on there, it dissociates completely into Zn2 plus and zinc ions, and SO4 sulfate ions, SO4 minus. Of course, you have the same amount of zinc ions and sulfate ions. That means that the solution to the outside is neutral, because there you have the same amount of, or the same number of positive charges than you have negative charges. Any solution that is neutral has to have the same number of opposite charges. Now, we take furthermore, we throw in that pot, what did I say, zinc sulfate, yeah? We put in copper sulfate. Copper sulfate is nice and blue. It is a salt. It dissociates completely into copper ions, into sulfate ions. Again, it's charged neutral in the solution. Same number of copper 2 plus ions, same number of sulfate ions. Okay. So now we put in a piece of zinc metal and just stick it in there. Take a piece of metal, stick it into the beaker. Okay. And then we take a copper metal, a copper rod, and put it in there in that solution. So now there can all kinds of things be going on. Either the copper metal can go into the solution and makes copper 2 plus. That's one possibility. Okay. The other possibility is the copper ions could go to that copper metal and come out as copper metal. If they get electrons, if you put in electrons through the copper metal, this will be reduced to copper 0, so it will plate out. That means the copper metal becomes more and more because you get out of the solution that these copper ions deposit on the copper metal as copper metal. The other possibility is that you have the zinc metal that you have there could go in solution and make zinc 2 plus ions. That's one possibility. Or the zinc ions that you have in solution can pick up some electrons and then become zinc neutral and deposit on the zinc metal. So the zinc metal will become heavier and heavier because the zinc would be depositing out. These are possibilities, but they are not possible, all of them. So what is possible? Now, if you write this reaction correctly, this is how that reaction happens. So the copper ions that you have in solution will, at the zinc metal that you have sticking into that solution, the copper ions will be reduced to copper metal, and the zinc metal that you have in the solution will start dissolving. It will go into the solution at zinc 2 plus ions. Okay, this is what happens here. So if you look at this, what would be the K of this then for this to happen? Now, what would be delta G naught for this to happen the way I have written it? What would be delta G naught? Negative. And with this, what would be K? Positive, larger than 1. Okay. So delta G naught is smaller than 0. Excellent, you found this out. And K would be larger than 1. All right. So that means the universe itself likes to have, if you have zinc and copper ions in solution, it likes to have not this in solution. It likes to have zinc 2 plus ions in solution and copper metal. All right. So this obviously is an oxidized form of copper. So, and the oxidized form of copper, what can happen? It's called an oxidizer. Anything is called an oxidizer that pulls electrons of something else. Okay. If this pulls electrons, it likes to get electrons, okay? So with this, it will put, let's say it pulls 2 electrons, and I can tell you already when it pulls the electrons off, it pulls it off the zinc, of course. It pulls 2 electrons off, and then it becomes copper neutral. And now, this is now a reducer, okay? This is the oxidizer, becomes reduced, and the reduced form becomes reduced and goes in this way. It can go in this way, and this is determined by some of the mechanisms that we are discussing today. So now, these electrons have to come from somewhere, and obviously the zinc doesn't want to be zinc, it wants to be zinc 2 plus, so it says, I want to get rid of my electrons, and the copper says, fork it over, okay? I want these electrons, the copper says, no, I want to be zinc 2 plus, the zinc says, I want to be zinc 2 plus, this is a reducer, and the reducer gets oxidized, goes in this direction, okay? So now we have where the electrons were exchanged, obviously 2 electrons, and this is your reaction here. So this is the half reaction, so that we can divide this in 2 reactions. One is the oxidation reaction, and the other one is the reduction reaction. So our oxidation reaction is obviously the zinc here gets into zinc 2 plus 2 electrons. And the reduction reaction is that the copper, that's our oxidation reaction, and the copper 2 plus, okay, that's already oxidized. It gets reduced by taking these 2 electrons and making copper 0, okay? That's the reduction. So we have an oxidation-reduction reaction. This is called a redox reaction. The oxidation is this here, and the reduction is this here, and I combine both of those. Now, obviously, this one goes in this direction as we have written it here, but this one goes also in this direction. No, this one goes in this direction, this one goes also in this direction. It's fine, we're okay. We both have the oxidation and the reduction at the same time. So let's have a look. So these are these 2 electrons, and these 2 electrons that are generated here will be picked up by the copper and reduce the copper from 2 to 0, all right? So we have seen that delta G naught is smaller than 0. That means that system can do work. But we don't allow it to do work. It does work into the solution. The electrons slip around there in the solution, and they change from the zinc, they go off the zinc and go on to the copper 2 plus, and that's all the work. It is useless work for us. But what happens if we make one solution where we have zinc sulfate and a zinc metal piece in the solution, and then we make another solution where we have copper sulfate and a copper metal piece sticking in that solution. So we have 2 beakers, and we separate them from each other. Now all what has to happen is that the electrons can flow between the 2 solutions, because the one wants to shed the electrons, wants to get rid of the electrons. That's the oxidizer that gets reduced, and the other one wants to have these electrons. And when we let this flow through a wire, we can use these electrons to perform work. They will power your cell phone. For example, the battery is not 2 beakers in your cell phone. It's a very sophisticated little battery, but it works after this principle here. So we have the oxidation here. There is my zinc metal, and there is my 1 molar zinc sulfide solution here, 1 molar zinc, and I have this piece of zinc sticking in there. And there I have the piece of copper sticking in a solution that is 1 molar in copper sulfate, okay? So here the oxidation happens. The zinc goes into solution and leaves 2 electrons behind here in the metal, all right? So that metal becomes negatively charged. And here, what should happen here? The copper goes into solution, but it needs 2 electrons to go into solution. So if you shoot these electrons over here, then it has these 2 electrons. These 2 electrons that were generated here by this reaction. The zinc is now in solution. This becomes less and less and less and less, and it makes puts zinc in solution, zinc 2 plus. And now these 2 electrons, they flow from here to here, and now this becomes negative. And with this, the copper says, okay, I'm picking up these 2 electrons. These copper in solution says, I pick up these 2 electrons, and now I can become copper again. And this becomes heavier, the copper metal, and this becomes lighter because this dissolves and this grows. And so you can use these electrons when they are flowing, you can use them to work. Of course, at one point, the zinc will be gone, and then it's your battery or your galvanic cell, which is called Galvani, was an Italian. He came up with this kind of a contraption, and he called it the galvanic cell. And so you can use that free energy, the delta G, to do work. And the work is you put a voltmeter here, for example, or you put a light bulb there, or your cell phone, or whatever you want to use your battery from. But this is the principle of a battery. So now I have it here again. These are these two electrons. They're flowing through that wire here into here. But now I make it even more difficult. Think about this. The zinc here goes into the solution. And here we have zinc sulfate in solution. But we don't add any sulfate. So as the zinc goes into the solution, it becomes more and more positively charged, okay? Because the sulfate is the same, so the charges don't balance each other anymore. The sulfate SO4 - against the zinc 2+. You're making more zinc 2+, and so there's not enough sulfate in there. So what do? You need to balance this somehow with another anion that you let flow into that solution. And then you have a salt bridge, and I'll talk a little bit more about this in a second. But I want to go to the reverse here. The reverse is that the copper goes into the solution, okay? No, the copper comes out of the solution. The copper comes out of the solution. Now your solution has too many negative charges because the sulfate stays behind. So there you need to put in positive charges, ions that are positively charged, and here ions that are negatively charged, all right? So you have a salt, it's called potassium nitrate, KNO3-, KNO3, dissociates in potassium, which is K+, and NO3-. And you put this in a salt bridge, which has sort of jelly in there, or agar, and you embed this in the jelly, and so there at this interface here, it sees that solution and says, that solution is deficient. Deficient on what? It's too negative or too positive, that solution? That's too positive. So I said, okay, the nitrate ions diffuse in there from the potassium, they diffuse in here, and make this charge neutral again. And here on this side, what is that, too negative or too positive? To negative, so you need to have positive ions. So the potassium ions, they diffuse into that solution, and this is charge neutral again, and this is charge neutral. So this only works if you have the salt bridge. If you don't have the salt bridge, nothing happens because this is not charge neutral, okay? So we have now, there it is. It goes from the negative pole, that becomes the negative pole here, okay? Because there is the zinc goes in solution, and with this the electrons are here, and this is more positive, they flow in here because it's more positive, and that's the cathode. And so we always have the oxidation when you draw something like this. The oxidation is on the left side, and the reduction is on the right side. And the reduction is cathode, and the oxidation is the anode. Very difficult to memorize, but you note this always at one of these galvanic cells. Is here's your zinc, okay? Then you have a dash, that's your zinc 2+ solution. You give it the concentration here. Then you have the salt bridge here, that's the double dash. Then you have the copper 2+ solution, it's 1 molar, and the copper metal. This is how you write this. That's a short notation for a galvanic cell. And if you now measure that potential, the difference between this and this gives you 1.1 volt. 1.1 volt, exactly. At standard conditions. And now the interesting thing is, this is one case where we don't have to mess with standard condition because it really works in standard condition. It's 1 molar. Both solutions are 1 molar at 25 degrees. It's at standard condition, okay? It was always strange when we had these reactions. Everything is standard condition. Everything is 1 molar reactants and products in order to see what happens with delta H or delta G naught and so on. But here it works in standard condition quite well, actually. That used to be Schatzi, my cat. And he died before the half of a heart attack. Don't worry about it. We have another one. But he was a really nice cat, and he was a red cat. There you go, a red cat. Okay. And this is another mnemonic. The mnemonic is for reduction is cathode. Cathode, what was that here? Let's go back here. Cathode was the plus pole, and that's where the reduction happens. So when you write the reduction reaction, you always use the right side. You think about red cat, the reduction is the cathode, and that way you're writing it perfectly. You couldn't care less about my cat, at least not as much as I cared for him. But, you're a great fellow. He was a feral cat, actually. We got him when he was 5 months. We got him from the Berkeley Pound. And he got very well along with our Scottish Terrier, so they were playing with each other constantly. Anyhow, red cat. Reduction is cathode, and with this now, we have the free energy. You remember we had the standard reduction, the standard potential that we can measure, okay? The free energy is minus n times F, and I forgot the delta here, times delta E naught, okay? To change the difference between two half cells. We call this as a half cell, and this is a half cell. Each of these half cells, and we tabulate the potentials, and then we can compare them, and I will show you how we compare them. We know if the potential is very positive, it goes from left to right. If the potential is negative, it doesn't go from left to right. It goes from right to left, the reaction in the table, and we get to this. Let's see Schatzi again here, and there we are. And so the N is the number of moles of electrons transferred, F is the Faraday constant, you know that, and delta E, and this is delta, there's a delta, is the difference in the free energy of the two half cells, okay? Not the free energy in the potential. That's can you measure, or you go and read it, get it from tables. So if this is positive, delta E is positive, that means delta G is negative, and that reaction will go that way as you have written it, okay? So the products are favored then. And so I think I need Karen now. Yes. So this is how you determine delta epsilon. Delta epsilon is, for example, the, what was that? The copper, so that means reduction minus oxidation. Reduction minus oxidation, or the potential for that on the right, that's the reduction side, the standard potential on the right, minus the standard potential of the left cell. That's the left cell is what? The oxidation or the reduction? That's the oxidation of the left cell. Oxidation means your metal goes in solution and becomes oxidized, okay? Is that true? Yeah, that's true. Okay, zinc goes on the left side. Yeah, good, okay. So, but we need to measure these half-wave potentials, these potentials here that I don't have it here. For example, copper plus 2 electrons gives copper plus. So I measure that against a standard hydrogen electrode. That's our reference system. If it's positive, then it's an oxidizer, and everything that is below the oxidizer or negative, doesn't have to be necessarily negative, is a reducer, okay? So the standard hydrogen electrode, so this would be, if it goes in this direction, so the hydrogen is oxidation state what? +1, okay? And we reduce it. This is what we do reduction reaction. It can also go if you have hydrogen, and it can be oxidized.